I have shamelessly copied everything in this presentation from your book and from everywhere in the web. So what I'm doing is I'm putting these links out here so that if you click on the link and not be satisfied with just this slide, you will find another what we say uh, bhandara of treasures or cornucopia of treasures, right? So you'll find a cornucopia of other material and more information if you go to that link, right? Of which I have just pulled out one diagram because that's relevant to what I am saying. But please do go to the link. Don't be satisfied, right? Like this man says, no, Shah Rukh Khan in Dish TV advertisement, santusht mat hona. So don't be santusht. Don't say this is the final diagram. No, 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 no. Please go to this link and read everything in this link, whether it is in the exam or not, whether a Subrat Kar tells you to read it or not, whether a Professor Dogra asks you to read it or not. Don't mind us. Get an education despite us, not because of us. Fine. So please go and read this thing and read anything else which occurs to you. Just like you keep on browsing on the Google and you go from one news to another news, please go from this page to another page. Feel free. Now, if you look at what is being said in this diagram, it says that there are these hardware vectors and there are these software vectors. All of them are actually um, restart instruction based uh, vectors, right? Except, of course, the INTR, which is the only non-vectored interrupt. So, whenever you do a restart-based vector, what really happens is that the restart expects you to go to a known location in the memory space. So, restart 4.5 will take you to 36D or 24H. So, 24H is where the address will be. This will tell you where to go. This will tell you where to go if RST 5.5 comes. Now, these restart instructions, I think I put another slide somewhere in my, let me see where I put it. Okay, I put this slide also in the morning today, just after. You remember this slide? I put this slide today morning. It says the call instruction and the restart instructions, right? So that both of them seem to be like jump instructions. They go somewhere in the memory and execute something. So if you say call and if you say restart, this will happen. So why two instructions? Well, restart, of course, goes to a known vector instruction. The call expects the address of the place you want to go to be told by the interrupting device. So there's a small difference. The restart is a 1 byte. Of course, functionally you can see that there is this relationship. So if I say RSTN, then it is same as saying call n into 8. And functionally that's what happens. Behaviorally, I would say, not functionally. Behaviorally, that's what happens. Uh, but the restart only takes 1 byte. So if you are going to frequently branch or there's a subroutine to which you frequently go, better to use RST or restart than call because call is 3 bytes, RST is 1 byte. Right? So it's faster. So in the INTR, right, you can only use a call because you expect that whoever is interrupting you will provide you the address. Like if you remember my story from yesterday's, the milkman told you go to the kitchen and in the second rack you'll find the milk vessel. So whoever is interrupting you is telling you what to do, right? So that's like an call instruction, right? But restart is like you know where to go. So that's the primary difference. But if you go to this link, you will find they are very similar. Now look at this. So let me put this. Okay, so let me put this marker here, and let me put a quick shape. All right, fine. This is a good marker. So if you look at the lowest priority interrupt, 7.5, it looks like this. So positive edge triggered. There's a restart 7.5. It goes into a D flip flop. So at the next, once you say that it is going to affect this queue, and suppose you have not masked the 7.5, then you will get this interrupt high and you will go to 3C16. Right? So 3C in hex. Similarly, if you have a RST 6.5, that's a level triggered. All these two are level triggered. Right? So then you will actually, if the mask bit is not set, then RST 6.5 and the mask bit inverted will take you to this address. Right? So you will find actually that uh, this is the internals of what happens when a trigger comes in. I found this diagram in the morning because I was trying to see, can I draw a consolidated picture of what I said in this slide? But this is a consolidated picture. This thing, if you see for the trap has no mask bit. You see this mask 5.5, mask 6.5, mask 7.5 is missing in the trap. It's a non-maskable interrupt. Fine. But in every interrupt, there is a third pin on this AND gate which comes from the interrupt enable. So only if this is interrupt enabled, so EI is high, set. So if it is set and disable interrupt is not set, reset is not set, interrupt recognized is not set, then this will enable these AND gates. So these three will get enabled and the INTR will also get enabled. But trap is a direct hotline to the microprocessor. Now look at this last one, the INTR. The INTR expects the RST code from the external hardware. So really speaking, I should say it expects the call code from the external hardware. So RST with address coming from outside is actually a call. So that is something which comes only in the INTR pin. So you will find dedicated pins like this and this one pin in which you can do a lot of things. So whatever, if you are not satisfied with a positive edge triggered, two level triggered, and a positive and a level triggered interrupt, right, then you can fulfill your heart with the INTR pin which comes from outside. So this was one slide which I found very nice. And if we go back to where we were, right, yesterday, we were here. I will, okay, you want to look at these things which I have said in these slides. These are the links out here, and I am cutting and pasting these to your chat window so that those of you who feel bored, oh, I don't have a chat window. Oh, because I'm a guest. Yeah, sorry. Guests on chat. All right, so you will have to just go to e-guide interrupt structure of 8086, 88. So these
slides you can share, na? So they can.
Yeah, slides I can share, but that's later. I can't do it right away, right? So maybe I have. Why these links are important is this is not the earlier link I gave. This is the interrupt structure of 8086. This is not the interrupt structure of 8085. So if you want to see what happened after the 8085, of course, what happened was 8088 came, right? And 8088 became 8086 with a small change in the data bus. And 8086 onwards, there were a lot of similarities. You will, as if you really have the interest to go and look at that, you will find that these RSTs actually amplified and became 256 RSTs. Right? Uh, these uh, these vectors reduced, right? Because then the committee said things are getting more complicated. We don't need actually dedicated pins we need to handle it in a slightly different way. And what they learned in 8085 and 8086 actually went forward. So if you look at the interrupt structure today in the i7 or the i5, you will find a lot of these things are taken from here. And not all of it, because we learn as we go along. So better, the newer microprocessors, the newer, more so-called modern microprocessors have expanded interrupt structures, better interrupt methods, slightly different architectures, right? The fact that some interrupts are local and some interrupts are peripheral generated, these things are taken care of in the new architecture which Intel gives, right? And that has become part of the microprocessor because microprocessors have become so big, isn't it? Just like when you have a small house, right? Let's say you have a one-room hut, right? Like when we were children, what we had in the in the ancestral home was a two-room hut. When you have a two-room hut, the functionality of the bathroom is across the courtyard. So you have to cross the courtyard and go to the bathroom on the other side of the courtyard. Right? But as your house expands, you know, this outsourced bathroom which you have on the other side of the courtyard slowly comes into the house. So you have an attached bath. Fine. So you have an attached bath, and then slowly every bedroom has an attached bath. So that becomes a part of the bedroom. And as the house expands more and more, let's say you have 7 sons, then some daughter-in-law will say, "Let me have an attached kitchen." So the kitchen then gets insourced and it migrates to a part of a bedroom. Right? So there is a kitchen one for daughter-in-law one, kitchen two for daughter-in-law two. So what you are doing is you're taking portions of the architecture which used to be central or external to the chip, and you are absorbing them into the chip. Then slowly what happens is you say that, oh, we don't want mix and match bathroom, kitchen. So let's have separate flats. So the different sons have different flats. So father on the ground floor, son one on the first floor, all have different flats. So then you say that, okay, we are inherently independent, right? But every once in a while we will go and tell you something. My wife will cook something and I'll give it to my mother. So there is some communication, there's some collaboration, there's some cooperation, but we are inherently uh, independent. So that's when we say we have a multi-core architecture, right? In which inside the same piece of silicon, we actually have portions which are almost independent microprocessors, almost, not quite, but almost. Every once in a while, they will cooperate. Right? And if they cooperate, they achieve more. If they don't cooperate, they are essentially independent families. I'm borrowing from this analogy of a family of father, son, daughter living in a set of flats, one above the other. And then it becomes, so you will see that 8085 is not the end all of everything. It is merely a ancestor or a progenitor of architectures like LAPIC, which you see nowadays in the i7. So APIC and LAPIC, right, these are the two architectures you will see in the i7. I have a slide at the end, which you will also see. But that's how things have changed. Now, so in short, what we are saying is, after this slide, what we are saying is, if the CPU polls for interrupts, it's a pretty devilish thing. So I've put a devil icon here, right, and I give it a thumbs down. But if I don't poll, if I interrupt, that's a good thing. But then as the interrupts go higher and higher, I think I should outsource this whole business of interrupts to a peripheral interrupt controller or PIC, right? So that PIC way is that all the IOs actually talk to the PIC. So you can see this. Ridiculous to get this laser pointer. You have to do so many things. I would have thought Microsoft would have given you some hotkey for laser pointer, Alt L or something. But anyway, so now the IO1 is connected to a peripheral interrupt controller, IO2 is connected to a peripheral interrupt controller, and ION is connected to a peripheral interrupt controller. And the peripheral interrupt controller should talk to the CPU through which interrupt pin? Now I think this answer should come from. Which interrupt pin is this pin? Is it trap? Is it RST0? Is it RST 4.5?
Should be INTR.
It should be
INTR.
INTR. That's right. It should be INTR because the moment this pin is asserted, we expect that this PIC will then tell us which handler to go to for this IO, which handler to go to for this IO. So we expect that it should first assert this pin INTR. Please note the word assert. When we say asserted, it means the pin is raised to its uh, the level to which it is supposed to be raised to make it active. That can be 1 or 0. So assertion of a pin does not mean raising it to 1. It means raising it to its active form. So if the pin is a active low pin, then assertion means driving it to 0. Right? So when I assert the INTR pin from the peripheral interrupt controller, the CPU, because it's an INTR pin, will then invoke the call, and the call subroutine inside the CPU will expect that the PIC or the peripheral interrupt controller will provide me quickly, not me, provide the CPU quickly with 2 bytes which define the address of the interrupt handler. Right? So that is the mechanism by which this outsourced interrupt will. Why did we say we outsource the interrupt? Well, that's because if there was only one IO device, you could have directly allowed it to interrupt the CPU. But since there is more than one IO device, we need a contractor, a interrupt contractor to handle all these interrupters. Right? So the contractor gets the call from the interrupter, and the contractor talks to the CPU. So in Odisha, we say Gumasta. So Gumasta is the contractor. So the PIC is the interrupt handler master. It handles all these IOs. The CPU doesn't know. Actually, the CPU doesn't know that this is the IO device. It'll never know because that is all handled by the PIC. So let's see what this PIC does. So there's this hero who comes in the 8085 called the 8259A. Right? It's actually the 8259. Right? The A is a slightly different version of the 8259. The difference is there in this data sheet at Renesas. So if you go to the renesas.com site and look at the data sheet of the 8259, let me search for this. Data sheet of the 8259. Very unlikely to find it. Very unlikely to find it. 825. I'll never find it when I'm searching for it. This is a variant of the Murphy's Law. Fine. Okay. What should I do? Should I go there? Okay, you will find it. It'll be somewhere there, of course. I think I have it. Okay. Ah, yes. God knows why I didn't find it. So if you have this 8259, once again, as I said, the data sheet is the most definitive source of information about any chip. So we go directly to the data sheet. We don't hang around Amateur or Smriti Sarangi and find out what they are saying about the 8259. Right? Remember my Chidananda talking about Bhagavad Gita? We don't want Chidananda, we want Krishna to talk about Bhagavad Gita. Interesting information here that these chips are all available in different packages, right? They're not the way you will see them in your lab, but that's not what we are looking at. So the most common one which you'll see in your lab is this one, but you get it in this format also. Right? The leaded chip carrier, plastic leaded chip carrier package, PLCC. Okay, so now if you look at this diagram, right? This diagram is where I copied my figure from, so that's exactly this diagram. Now I copied that figure, and like any copier, I immediately colored it so that you can easily see, following my color code for data, status, and control, that all the green portions are control. Everything here is control, the green one. I am not sure whether I should have put this yellow thing as also as control, because that's actually control. I should have made this control, but all right, when you see this, mentally color the yellow one as control, because this is all control. Maybe I made a mistake here. I didn't think about it so carefully, because there is no real status out here. Right? This is control. So I think if I can go back out here, I think I should change it to quick style control. Right? So sorry, quick style control. So that's control. All right. So that's control. There is no status register in this. There's nothing saved. Probably the only one here is this one. So I think maybe I could make the IRR as the status register, because that would be, but then I would have to actually make a little bit of complication like this. So I would have to say this is control, this is control, this is status. So quick style, this is status. Fine. So that is more correct. At least it is something to do with storing a condition of this chip. So not very well drawn, I'm afraid, but still more correct. So this 8259 can handle 8 vectored priority interrupting sources. Oh, what does that mean? That means that if I look at this, this will accept, and where does it accept? Unfortunately, that part is not very well, not very visible out here, but you can see these 8 interrupts on this side of the interrupt request register. Those are the 8 interrupters. So if you look at this diagram, the PIC can be connected to 8 IO devices directly. It can be connected to 8 more PICs. Right? So a PIC can be connected to a PIC. It's like having a first level contractor and a second level contractor to handle workers. So naturally, the first level contractor will only talk to 8 second level contractors. But each of the 8 second level contractors can have 8 workers. So in all, you can have 8 contractors into 8 workers each, is 64 workers. So that's what is being said here, that you can actually connect a PIC to another PIC, right? And there is a very nice hardware construct out here called Cascade 01, Cascade 0, Cascade 1, and Cascade 2, which allows this to happen. Now you see, if you imagine a first level and second level contractor, okay, so if you imagine that this is the CPU, and the CPU talks to a first level PIC, so that's the first level, and each of the PIC inputs is connected to a second level PIC. Shall I call it A? And or shall I call it, maybe call it PIC 11, and then I have a second level PIC and up to 8 PIC, what shall I call it, 1, 8. So there are 8 PICs here and they are all connected to this PIC. Right? And to each of these PICs, I have an interrupting device. So all in all, I will have the last device will be IO 64. So 64 devices can do that. Now, between this PIC and this PIC, there is a private bus. Right? So there is a private communication between this, which is defined by CAS 0 to 2. Right? So if PIC1 wants to talk to PIC2 or PIC11 or PIC18, it does so through this fellow, like this. The CPU doesn't know. This is the first level contractor talking to the second level contractor, and that is these 3. So you know there are going to be 8 second level PICs. So you only need 3 wires to connect and address those second level contractors. Now, what will happen is that if you don't have if you have only a first level contractor, that is, you have interrupt requests coming directly, then one or more of the IR request lines will go high. The 8259 will evaluate those requests and send an interrupt to the CPU. The CPU will acknowledge the interrupt and respond with the interrupt acknowledge low. After receiving an interrupt acknowledge low, the highest priority interrupt service register is set and the corresponding interrupt request register bit is reset. Which means reset means I'll now accept interrupt from that input again, but I'm currently doing this ISR. So suppose I get an interrupt on 1, I will set the bit 1 on ISR to 1. Moment I do this, the 8259, the PIC, will release a call instruction, right? Now, actually speaking, it could have released any instruction. At that point, whatever is released into the data bus, the CPU doesn't actually know. So you can release any instruction, but since we are gentlemen, we do not release any instruction. We release the call instruction because we are releasing this instruction for a purpose that the interrupt handler will be invoked, right? But if you want to really break a CPU, you can actually put any instruction there, not just a call, right? So you will release a call instruction. The moment you put a call instruction on the data bus, the call instruction will make the CPU issue 2 additional interrupt acknowledge pulses, which will be sent to the 8259. So this call will expect the first in the first int acknowledge, the first byte of the address will go into the data bus. After the second interrupt acknowledge, the second byte of the interrupt will go into the. So the lower 8 bits will release at the first interrupt acknowledge. The higher 8 bit will release at the second interrupt acknowledge. Once this is happening, the 3 byte call instruction is now complete. The ISR, which had been set at this point, will be reset. Otherwise, the ISR will remain set till the end of interrupt command is issued at the end of the interrupt sequence. So once the ISR is set until the EOI comes, right, you will not accept any further interrupts on that interrupt. So this happens automatically. This automatic end of interrupt mode, AEOI. AEOI means automatic end of interrupt. The ISR will be automatically reset. Otherwise, it will be reset only when the EI command is issued by the CPU. Now, in the 8086, till here, it is the same. After this, only a single interrupt acknowledge needs to be given by the CPU. And can you tell me quickly why this would be necessary? Why a 8086 CPU would issue a single interrupt acknowledge and why a 8085 would need two interrupt acknowledges? If there's a hint to be given, the 8085 has a 8-bit database and the 8086 has a 16-bit database. And what you are putting from the IO device is a 16-bit address. So does that give you a clue? The 8086 will give the interrupting device a full 16 bits to place the address, so it doesn't need to do it twice. But the 8085 has a 8-bit address as the 8088, so it will give two interrupt acknowledges. Right? So that's a simple mode. Then what happens if you cascade? Right? Somebody will say that 8 IOs are not enough, I need more, but we have only one INTR pin. So the 8259 is built to be cascadable. So you can have one master and 8 slaves. So this one master is the level 1 contractor. The 8 slaves are the level 2 contractors. They are the slaves of the level 1 contractors, right? And each of these slave PICs can handle 8 priority levels each. Now, what this actually does is the first level contractor or the master PIC controls the slave PICs through the CAS2 to CAS0. So CAS0 is the LSB, CAS2 is the MSB, most significant bit. And if you put, for instance, 001 in CAS2, CAS1, CAS0, it means you are selecting the PIC 001. So it's like a chip select for the slave number 1 during the INTA sequence. So suppose I have selected slave number 1, then when the CPU asks for the address, slave number 1 will release the address of its interrupting device. That's like saying that I have a, let's say, an interrupting pin. Let me draw it with a Django line like that. There's an interrupting pin like that. Sorry, I have to actually wipe this off and wipe this off and make it a little correct, because this is CAS2 to CAS0. Right? Anyway, you know this notation. This notation actually means CAS2, CAS1, CAS0. This is a lazy man's notation for, a lazy man's is a humorous term. This is the IEEE notation for CAS, for any bus naming. And we have an interrupt happening, let's say on pick 3. So this is slave pick 3, so I call it pick 1-3. So when this fellow is happening, this IO is happening, the pick 1, which has raised the interrupt to the CPU and has got the INTA from the CPU, will put on this a 011. Right? A 011 will select this pick as the fellow who is connected to the data bus. And remember, all these picks are actually connected to the data bus. So except that they are not all selected at the same time. So if you look at this, all of them are connected to the data bus. But the moment you select this pick, the moment the CPU puts the int acknowledge, it is this pick which will then step in and through the data bus, it will put the address number 1, and then again through the data bus, it will put address number 2. Right? That's a very fat 1 and 2. Did you make out that this is a 1 and this is a 2? Right? So it is this pick which will now interact. This pick which will now interact with this CPU. So this is how the cascading of the picks actually works. This was the mechanism in 8085 when interrupts were few and you had to cascade and feel happy that, okay, this at least this exists. But nowadays in 8086 and above, 256 interrupts can be uh, acknowledged through the same interrupt line. So you don't actually need to cascade interrupt controllers. You might still need interrupt controllers. I'm not saying you don't need interrupt controllers, but you may not have to cascade them because 256 is a very large number for a IO device set. Right? But there will be places where you may have to actually cascade and connect something like 60,000 devices. Right? One good example is these nuclear physicists and their experiments. Right? Nuclear physicists, are strange bunch of people. They dig a tunnel into the ground, right? 3 kilometers, 4 kilometers into the ground, and then they wait for something to happen, a nuclear event. So, and these nucleons, subnuclear particles, are very reluctant particles. They break apart once every 100 years or 150 years. So, if physicist one starts an experiment, it may be his grandson who sees the actual event. So, what they have is they dig this tunnel and they put a lot of instrumentation, a lot of detectors and ionizing detectors, and they keep waiting. Right? But the entire, you don't know in which direction this particle will go, so you keep these detectors all around the tunnel, thousands and thousands of them, so that whichever way the particle goes, you will still catch it and detect it. So suppose you started your nuclear experiment, detection experiment in 1800. Sometime in the 2022, right, you will get a nuclear event and a nucleus will split. And this is just before you get the Nobel Prize, of course. The nucleus splits, and these, let's say, 900,000 detectors, one of them detects that event, and then you catch it, and then you publish it, and then you get the Nobel Prize. But these 900,000 detectors have to be connected to a CPU. So there you come into a problem of how to connect 900,000, 9 lakh IO devices. Then you have to do some special things. You still need a programmable interrupt controller, right? And very fast ones. But that's where you need it. But in most modern situations, like MS Word and WhatsApp, and which is where our modern lives revolve, you don't need so many IO devices, right? Instagram, WhatsApp, such very modern, useful tools which our engineers use, we don't use that much. But all those vague tools which nuclear physicists use, which only are good for Nobel Prizes, those tools may use IO devices which are numerous, that numerous, right? I hope nobody is taking me seriously. That's a danger. Is anybody taking me seriously?
Yes.
You are. Please don't take me seriously. I meant it as a joke. There are very serious professional usages of IO devices, which are many, but typically in a PC, laptop, embedded system, we don't have lakhs of devices. So 256 is an adequate number. Take that part seriously, disregard the rest of it. Why do you take me so seriously? Or you don't have a sense of humor? All the people from Odisha have a very big sense of humor, because if we stop laughing, it's very difficult to live in Odisha. So we have a very good sense of humor. Okay, now cascade mode. So let's skip this and go to the classification. So there's a nice diagram. I pulled it together for the 8085. So priority wise, the highest one is trap, right? And this is of course what we call a mind map. Please look up the mind map of interrupts. So look up this term mind map. You will find it a very useful tool for taking notes. Priority wise this, vector, non-vectored wise. The vectored ones are this. You can call trap as a vectored 4.5, but I have not. Non-vectored, the only non-vectored is interrupt. Hardware-wise, the maskable interrupts are these, and the non-maskable. This is actually non-maskable. The block is too small. Okay, non-maskable interrupt is this. Fine. Then normal interrupts are these, only 8. And you can have periodic interrupts, aperiodic interrupts, synchronous interrupts, asynchronous interrupts. What is a synchronous interrupt? Something which happens with the positive or the negative edge of the system clock, like a timer, right? I have forgotten what the timer chip is, but there are timer chips inside 8085s. You can have a timer chip which counts down on the system clock, and when the count reaches 0, it gives you a ping. So depending on that ping, you can do something, right?
8 to 5 or 5-1. 8 to 5-1 or 5.
8 to 5-1. Okay, so 8251 is a timer chip. It has a counter. So you load the counter with a value, whatever value you want. You can load it with 2, you can load it with 32, you can load it with something else, but it will start counting down, and when it reaches a 0, it says, hey, I reached 0. That hey, I reached 0, the CPU may do something, may not do something. So you may have a timer based thing. For instance, let's say every 64 seconds you issue a signal to some device. Well, the timer will remind you every 64 clock ticks, not seconds, clock ticks. Every 64 clock ticks, it will tell you, hey, I reached the countdown. Now I'm going to count all over again. It's very dumb, so it does keeps on doing that. So that's a synchronous and a periodic interrupt. And it should actually use one of these RSTs, because if it is interrupting you every 64 clock cycles, it should have a very short and sweet interrupt handler. You can't have a 3-byte interrupt handler, right? And in some classifications, we call these black ones, right, as first level interrupt handlers, and we call the remaining as second level interrupt handlers, because second level interrupt handlers are normally called from inside a software program, right? The first level ones are usually called from outside, and Atithi Devo Bhava, so whatever is coming from outside must be given a first level treatment, and whatever comes from inside will be given a second level treatment. So we say this is a second level interrupt handler. I don't think I can think of any other reason why this should be called second level and that should be called first level. So for the moment, this will have to suffice as a good enough reason for calling this first and calling the other one second. Okay, so at this point, we are ready to go next week into hardware for I/O, right, which is buses and protocols for I/O. So any questions? We are at the end of this class. Any questions? I seem to have a link. Oh, okay. There is a link to that other slide. And there is nothing after this. If any of you are wondering what are the 2 slides I'm jumping, these are the 2 slides I showed somewhere in between. I kept them after this because these are not very relevant to what I was saying. I've kept them after this. So there's nothing suspenseful about this. I'm surprised. Yesterday in a slide, I had kept a very jazzy thing which nobody commented on. Okay, this slide. Nobody commented on this one. Did you see this little icon there? I thought it was a pretty jazzy thing, but nobody said anything. So I'll just not explain this. It was supposed
That music icon.
Huh? It's a music item. I had said an alternative approach is to use vectored interrupts. Hold your breath till the next slide. And then I had thought when I was making this that I should place my mouse over this and it will say dark, meaningful music soundtrack should play here, appropriate to the suspense surrounding the mystery of vectored interrupts. Right. So when like when somebody is going to get murdered in a movie, the background track already warns the audience that expect a murder in the next 5 seconds. So I had thought I would do this, but nobody asked. I forgot. So end of suspense, that was an anticlimax. Only when I was reading it in the evening, I said, "Oh, I missed out one nice part which I had entered." Now you see one thing. Right? I don't know, but you might be used. You must be accustomed to serious teachers. Are you accustomed to serious teachers? Very, very solemn, unsmiling, stern looking teachers who tell you, unless you work hard, you will not do well. Are you used to such teachers? Professor Rajakumar is like that. He keeps telling people, work hard, otherwise you won't survive. He's a very serious person, Professor Rajakumar, your director. Yes or no? You are all too afraid to say yes. But you can say yes. He is a serious person. But anyway, the entire point is, unless you have fun, unless you have a lot of fun, learning doesn't start. Learning cannot start under the shadow of fear. Learning only starts when you start enjoying what you are learning. And if you start enjoying what you are learning, no teacher in this world can stop you from learning. That is a secret. So, having fun is not a sin. Working hard is not necessary. Working right is necessary. Reading right is necessary. Reading the right way is necessary. Not reading long hours, not reading for 12 hours in a 24-hour day, not that way. No, no. You read the right way, enjoy, discuss, use, try to envisage and imagine where I could use this, right? And you will immediately feel like a more useful engineer all the time. You will not have those typical doubts which you have in third year that, God, what am I learning? Am I learning anything at all? I need to go to Paris and do an internship in so and so institute to actually learn what I'm not learning here. Those doubts will never come to you if you have fun. Because once you start having fun, like for instance, you like watching Netflix. So why do you binge watch Netflix? Because you're having fun, right? Nobody's telling you to watch the next episode in the serial. So why do you watch 40 episodes? Why do you not go to the bathroom and watch 3 episodes at a run? Because you're having fun, right? So start having fun. Don't listen to things like, unless you study hard, you will never make it in the world. Oh, my other class is starting. So I will go and have more fun for 50 minutes. They are also another bunch of undergraduate students, right? Not as punctilious, not as punctual, not as regular as you are. In a class of 73, I see 74 attendees, right? But nonetheless, young people like you. So I'll go for another hour of fun. Please have fun.
But this is a nice lesson actually, sir. You have given this to students. I also, like this the way of teaching, like you are adopting. This is students must also enjoy their learning. Okay.
Yes, you must enjoy. You must compliment each other, and you
Right.
must talk to each other. You must see what you can do together. Right? Never
Right.
hide something you're doing from somebody else. Throughout our childhood, we are taught, if you're answering a question, put your hand at the top of the question so that nobody sees what you are writing.
Sir, just 1 minute. This semester, I was doing an experimentation. I asked the students to self-evaluate their midterm marks, midterm copies. Okay.
Absolutely.
Surprisingly, I found that my evaluation and student self-evaluation are almost similar, with a maybe +1, -1 changes in some cases. Average maybe something like that.
Mm-hmm.
So, you know, I was telling the students that if you enjoy your, writing, or if you enjoy your answering, then you must evaluate yourself. Okay. So,
Absolutely, yes, I agree. I agree. And that is the most honest evaluation you can ever have, because that is
exactly. So,
that
so,
is
so
not
I
colored by my
anticipated.
experiences.
Yeah, I'm surprised that students have actually, many of them have evaluated perfectly what I wanted them to get. Okay, so I'm really happy that some of them are really enjoying, but obviously we as a mass, I want all the students to enjoy this class.
Yeah, true. Right. Bye. Goodbye. So I'll see you
Thank
on
you.
Wednesday.
Yeah,
Thank you, sir.
thanks.
Bye.
Thank you.